start the recording. Right, so where are we in our class? We've tackled the definition of integration last week. We looked at a couple of examples and we started looking at techniques to tackle ever more bigger classes of integrals. And I will share my screen. Where were we at the end of day on Monday? So on Monday we did we looked at integration by substitution, and we also looked a bit at trigonometric integration. And what we're going to do today is cover the rest of trigonometric integration, integration by parts, and then we'll also look at these so-called reduction formulae, which are situations in which you don't find the integral right away, but you find a formula that helps you solve the integral. So first, let me skip over substitution. We did that last. I just want to add one more example to get things in our head. So let's do one more quick example of integration by substitution. So let's have a look at, for instance, the integral of sine 3 times ln x divided by x dx. This is a prime candidate for integration by substitution because you see that ln x, so if you call that t, so if you put t equal to ln x, then dt is going to be the derivative of that, so 1 over x times dx, and you see that dx here combines nicely with 1 over x to give us dt. So for instance, in this case, we get that the integral becomes sine t dt. So sorry, not sine t, sine, and actually I need to, let's do it just a little bit more careful. So I get sine 3 times t dt. And now this is maybe not an integral that we can solve directly. That's why I needed to be a bit more careful, but it's going to work anyway. So now I can call this 3t. I can say this is u. So u is 3 times t. du is 3 times dt. And finally, my integral becomes 1/3 sine u du. And that's, of course, something that we can integrate. We get minus 1 over 3 cosine u plus a constant. And now we have to write that as a function of x. So the first thing that we can do is we can get rid of the u, write this as cosine 3t plus a constant. And now the second thing is, this is still not a function of x, it's a function of t. So let's back substitute t is equal to ln x, and we get minus 1/3 cosine 3 times ln of x, logarithm of x plus a constant. And here it would be really easy to take the derivative again and check that we have sine 3 ln x divided by x, just as a check, but I'll leave that to you to do. The main message with integration by substitution is, yeah, you have to look a bit in the integrand for what you already have and what you can substitute. So with that, let's scroll forward to what we were doing at the end of Monday. We were looking at trigonometric integration, where we basically substitute with the trigonometric function. And we already did a few examples, some easy, some not so easy. So let's do a few more examples. Let's have a look at the integral of, and let's see which, this is example number 5. So let's look at the integral of sine to the power 3 of x times cosine to the power 8 dx is equal to, let's try to find it. if you have an integral with sine and cosine, you'll see this in the examples that will follow. Have a look at the powers. If you have an odd power somewhere, then chances are that you will be able to use trigonometric substitution. So here, in particular, we have this power 3 here. This is an odd power. So this is good for trigonometric substitution. And why is that? Well, you'll see in a minute. So what we can do is when we have that odd power, we can write it as sine squared times sine. So we split off one of the signs and we leave the rest as it. So we leave cosine 8 to the power 8 dx. And so now if let's ignore this sine squared for a second. If I just had sine x cosine to some power, let's call it n dx. Now you probably see what you have to do. Now here you could substitute t equal to cosine x, and then dt becomes minus sine x dx, and this integral turns into minus t to the power n dt, which you can solve. So minus t to the n plus 1 divided by n plus 1 plus c is dot. So if this was the integral, we would be able to solve it, but it's not. It's sine squared times all of those terms. So before we can move on, we need to do something, and the right thing to do here is to write everything as a function of cosine x. So let's write the sine squared as 1 minus cosine squared, because then what we end up getting is, if I work everything out, I get cosine to the power 8 minus cosine to the power 10 of x times sine x dx. So all I've done is I've reorganized the terms a bit. But the upshot is that I have something complicated involving cosine and then times sine x dx. And now I'm going to use my trigonometric substitution. I'm going to put cosine x, I'm going to call that t, and then dt is minus sine x dx. And so that works out nicely, because now I see I have a minus dt here, and I have a t to the power 8 here, and a t to the power 10 here. And so if I write that down more clearly, I get t to the power 10 minus t to the power 8 dt. So remember, it's minus dt here, so it combines the minus here to give me t to the 10 minus t to the 8. And now that I can solve, that is t to the 11 divided by 11 minus t to the 9 divided by 9 plus a constant. And now back substituting gives me cosine to the power 11 of x divided by 11 minus cosine to the power 9 of x divided by 9 plus a constant. I will give you another example to try by yourself. And make a bit more space here. So example number 6 is cosine to the power 5x dx. And so again, notice how you have an odd power here. So what that allows you to do is that allows you to write the integral as cosine to the power 4 times another cosine dx. And that cosine x dx, I'm going to leave that aside. I'm not going to touch that. Where's my brown pencil? This is going to become my dt. So now I'm going to need to substitute something, and I want to make a substitution so that dt is equal to cosine x dx. So I'm going to have to look for t is equal to sine x somewhere. But if you look at the integrand, I don't have sine x anywhere. I have a lot of cosines, but I have no sine. So that means that we have to rewrite the integrand a little bit. And what we can do, for example, is we can turn cosine to the power 4 into sine by writing this as 1 minus sine squared of x squared and then cosine x dx. And now it's clear what I have to do. Now I can make my substitution that I've already indicated. I can say, well, sine x is t, or sine squared is t squared. And then dt is cosine x dx. And so what I have here is dt. And that lands me with 1 minus t squared dt. And if I expand that, I get 1 minus 2t squared plus t to the power 4 dt. And then I can integrate to t minus 2/3 t to the power 3 plus t to the power 5 divided by 5 plus a constant. And now if I plug sine x again, I get sine x minus 2/3 sine to the power 3 of x plus 1/5 sine to the power 5x plus a constant. The critical thing here is to realize I have an odd power of my trigonometric function, so I can split off one cosine, and then I have to do something to the remaining part of the integrand to be able to prepare it for my substitution. And here, so if I split off a cosine, I'm going to want to substitute by sine, because the derivative of sine is cosine. And that means I have to write my entire integrand, my cosine to the power 4, as something involving only sine. And fortunately for us, that's easy because we know cosine is 1 minus sine squared. And therefore cosine squared squared, or cosine to the power 4, is 1 minus sine squared squared. So if you have an odd power somewhere, then you're typically home free. You can use this kind of splitting up the integrand. But now what do you do when you don't have that? So for instance, what if we have to integrate cosine squared of x dx? So this trick that I mentioned before of splitting off a cosine is not going to work here. If we write this integral, and I'll just write it down, if we write this as cosine x dx, and now we try to make this into dt, then there's nothing really here that we can substitute for. So our approach of the previous slide is not going to help us here. So let me maybe just scratch it out. That's not going to work here. What we can do instead is we can use our formulas from trigonometry. And in particular, we know we can rewrite cosine squared x as 1 plus cosine of 2x divided by 2. So we can use that here to write the integrand like so. And now we can integrate each part in turn. So we get integral of 1/2 dx plus integral of, actually, let me write this as integral of dx multiplied by 1/2, because it makes it a bit easier to look at, and then 1/2 integral of cosine 2x dx. So integral of dx, integral of a constant function 1, that's going to give me an x, and then plus 1/2, and now the integral of cosine 2x. So here we need to do one small substitution. Let's write 2x as t. So dt is 2 times dx. And that gives us the integral of cosine t dt divided by 2. So we get 1/2 x plus 1/4. And now the integral of cosine, that is sine t plus a constant. And now we can write everything as a function of x, 1/4 sine of 2x plus a constant. And so you see, in this case, we had to use one of our trigonometric formulas. We didn't have to make a particular substitution except for this constant term, but that's easy. But we didn't have to do a trigonometric substitution. Likewise, I give you another example. The integral, for instance, of sine to the power 4 of x. Here, what you can do is you can write this as sine squared of x squared dx. And okay, now let's continue this part over here. What is that equal to? Well, for this integral, we can use the fact that sine squared is 1 minus cosine 2x divided by 2. So you can write this integral as 1 minus cosine 2x divided by 2 squared dx. And this is now a little bit painful because, okay, now you have to work out what is inside this square, and you get 1/4 1 minus 2 cosine 2x plus cosine squared 2x dx. And the first two parts are easy. So we get 1/4 and then the integral of 1. That's going to give us an x. And then minus 2 times the integral of cosine 2x. So I've already done that when I did example number 7. So the integral of cosine 2x dx is going to be sine 2x divided by 2. So if you take the derivative, you see that that works out. So get minus 2 times sine 2x divided by 2. And then we still have, and I'm going to leave it explicit like this, we have the integral of cosine squared 2x. And so now we have to figure out what that is. Excuse me. And so in order to do that, we can use the results that we obtained earlier. So I'm going to leave some space here and fill that in. But I'm going to need one more line to do one auxiliary computation. So what is the integral of cosine squared 2x dx? So let's bring it in a form where we can use expression number 7. So let's call this 2x, let's call that t. And then we have that dt is again 2 times dx. And therefore, our integral becomes cosine squared t dt, and then times 1/2. And now I can use directly my results from the previous step, from 7, to say this is going to be equal to 1/4 t plus 1/8 sine 2t plus a constant, or as a function of x, t is 2 times x, so x divided by 2 plus 1/8 sine 4x plus a constant. Okay, let me just double check that that's right. So x over 2, 1/8 sine 4x. Okay, so that gives me my integral here that I had to compute. And now I can put everything together. So you can plug the results that we just obtained in this expression. And then you'll see there's some x's that combine, and you'll have a term sine 2x and a term sine 4x. And when you do all the simplifications, you will get that the result is 3x divided by 8, minus sine 2x divided by 4 plus sine 4x divided by, in this case, 32. So you'll get you have the 1/8 here, and then a 1/4, and those combine to give you a 32 instead. Plus, of course, an arbitrary constant. So just to make it clear, let me put it in a frame like so. This is our final answer. You see the same basically rule at play. We had an even power here, so we couldn't use a trigonometric substitution right away. We had to use our power formulas to reduce the power of sine squared, and then we had to actually do that twice, once for sine squared and then another time for cosine squared here, until we had the result. And let's do maybe one more example before we move on with that. And let me actually leave that up for just a second while I have a look. So for the last example, which one is this? This is example number 9. Let's have a look at the integral of tan squared x dx. So this is also not something where we can make a straightforward trigonometric substitution. So if you can't make that substitution, then what you have to do is basically use formulas from trigonometry to bring the integrand in a form where you can more easily solve it. And one of the things that we can do here is we can say, well, okay, I don't know what the integral of tan squared is, but I can work with tan squared, and I can, for instance, write this as secant squared of x minus 1. So why is that true? Well, secant squared is 1 over cosine squared minus 1. So we get 1 minus cosine squared x over cosine squared x. So we get sine squared divided by cosine squared, which is, of course, tan squared of x. Okay, so let's use this formula and let's plug it in and see if that gives us anything. And at this point, well, I've got an integral of -1. That's easy, that's minus x. But I also have an integral of the secant squared function. And that is a good thing, because if you remember from way back in the beginning, we said, hey, the derivative of the tangent function, derivative of tan x, is 1 over cosine squared, so is equal to the secant squared of x. So conversely, the integral of secant squared x is the tangent function itself, so it's tan x plus a constant. So you see, it's maybe not something that you would think of right away, but if you remember what the derivatives are of the 6 elementary trigonometric functions, then you can also recognize their integrals again. And so what we get is here for the integral, we get integral of secant squared minus the integral of x, integral of constant function 1. Now we can combine these two results, we get tan x minus x plus a constant. And then I'll give you one more example to do by yourself. The integral of secant to the power 4 x dx. So here too, you have to use some trigonometry. And one thing that I will tell you is that it's a very good idea to write this as secant squared dx. And then here to turn this secant squared into a 1 plus tan squared x. And then why is that going to be a good idea? Well, if you make a substitution, t equal to tan x, dt is going to be secant squared x dx, and therefore you're already like you will have something. So let me maybe just wrap this up with a few notes. So here, if we substitute t equal to tan x, what is dt? The derivative of tan x we had here, so that's secant squared x dx. So you get that this becomes dt, and this right here, or I should write it down below, is 1 plus t squared. So then you'll end up with an integral of 1 plus t squared dt, which you can integrate, it's polynomial. And then if you back substitute, you'll get that this is equal to tan x plus 1/3 tan to the power 3x plus a constant. I leave the remaining steps to you. If you have any questions about this, feel free to reach out or to send me an email. Okay, so then let's see where we are. So that concludes our trigonometric integration. So now let's talk about integration by parts. This is also a very common technique where to sort of turn your unsolvable integral into something that is maybe solvable. And right off the bat, I'm going to say none of these techniques stand on their own. It's very rare that you can just use one technique and be done. It's always a combination of things. So let's first talk about what this rule tells us, how it works, and then we'll see a couple of examples. So I want to give you an intuition for what this rule is and why it is true. But in practice, you don't have to know this to apply the rule. So what I want to... Sorry, there's someone's microphone still on. Okay, thank you. So first, let's start with some intuition for why this rule would hold. And let's start with taking two functions f and g. And let's take the derivative of the product of f and g. And as you know, well, what is the derivative of a product? Well, it's the derivative of the first function times the second plus the first function times the derivative of the second. So this is something that we know from derivatives. And now let's take the integral of both sides. So I'm going to take the integral of the left-hand side, and I'm going to take the integral of the right-hand side. So integral of both sides. And so what I end up with is integral of d dx f g dx, and that is equal to integral of f prime gx dx plus integral of fx g prime dx. Okay, and now let's focus a bit on this left-hand side. So what do I have here? I have an integral of a derivative, and I said, hey, the integral does the opposite of whatever the derivative does. So if you take the derivative first and then you integrate again, that's the same thing as doing nothing. So here, if we take the integral of the derivative of f times g, we get back our product f times g. And now you might wonder, well, why don't you write plus c here? Don't you have to include that? Yes, you do. But I will omit it because on the right-hand side, I have two indefinite integrals. And when I calculate those, they're going to give me my c. So I can absorb that constant in my integrals on the right-hand side. The important thing here is on the left-hand side, what I basically end up with is the original product that I started from. And now let's rewrite this expression a bit as follows. And this is going to become our rule. So let's take the first term on the right-hand side and put it on the left-hand side. So let's take f prime times g and then take the derivative of that. So what is that? Well, it is f of x, g of x. And now I have to take this integral and bring it to the other side. So I get minus f g prime dx. And so let's look at this for just a minute. So what does this tell me? So if I have an integral of a derivative times a function, I can write that as another integral of that function times the derivative. And I'm going to try to do that if the integral that I get on the right-hand side is a little bit easier to solve. So typically, you would use this when the function f by itself is easy to integrate and the function g is easy to differentiate. Because you see, if I want to apply this rule, I'm going to have to take g prime, the derivative of g. So I want to put something here that's easy to differentiate. If I can't calculate the derivative, can't even apply the rule. This is a bit vague, but we'll see a couple of examples. And just before we go to the examples, I want to give you an easy shorthand to remember this. So you'll often see this written down in short as the integral of u prime v dx is uv minus uv prime dx, or even some people write it as v du is uv minus u dv, but personally I do not use this notation. So so basically what they do is they combine the u prime dx into du and the v prime dx into dv to make it even more short, but I will not use this notation all the time. So that's our integration by parts rule. Why is it called by parts? because if you look at the integral, we don't solve the whole integral. We just turn it into a different integral by integrating the f prime. So we only integrate a part of it, therefore integration by parts. So let's look at a few examples, and let's start off by a very famous example. Let's compute the integral of ln x, the logarithm function. So first of all, if you want to apply integration by parts, you always have to identify two things in your integrands, an f and a g, or in the other notation, a u and a v. So remember, our rule is u prime v dx is uv minus uv prime dx. So we need to figure out what is u prime and what is v in my integrand. And that poses some problem because here I have ln x. I don't have anything else. So how can I make two things out of ln x? Well, one thing that I can do is I can say, well, this is actually 1 times ln x. And now I have two things. And now the second step is I always want to write, I want to choose for u prime the thing that is easy to integrate, because I'm going to have to turn u prime into u, and that's going to involve an integration step. So I want to choose something that's easy to integrate, and 1 is definitely an easy function to integrate. So let's call that u prime, and then ln x becomes v. And so now what is, and let's maybe just for this once, let's write it out, everything in full. So u prime is 1, v is ln of x, and therefore we can also write down what is u. So if the derivative is 1, then the original function was x. And if v is ln x, the derivative is 1 over x. So now I can use my formula. I can say, well, I get u times v. So x times ln x. In other words, u here and v here. And then minus, and now I get the integral of u v prime. So u is x, and v prime is 1 over x dx. So here we have u again, and here we have v prime. And now, of course, we see that this looks quite nice because we get x ln x minus integral x and 1 over x, they cancel, so I just get integral dx. And now I can finish off x ln x minus x plus a constant. And I can also write this as x times ln x minus 1 plus c. Okay, if you've never seen the integration by parts rule before, then keep in mind you have to find two things in your integrand. One has to be easy to integrate. There's no easier function to integrate than the constant function 1. And the other thing has to be easy to differentiate. And here ln x is easy to differentiate because we know the derivative is 1 over x. If you had chosen it the other way around, so if you had chosen u1 to be v, and then u prime to be ln of x, then you would not get any further, because now you would again have to integrate ln of x to find u, and that's the whole point of the exercise that we're trying to do. So that wouldn't have helped you. So if you try to apply the rule and you can't integrate the thing that you've called u, then it means that you're on the wrong track. So that's one example. Let's do another example along the same lines. So let's have a look at the integral of the inverse sine function. Again, we're going to use the same trick. We're going to write this as 1 times, and now we have to choose our u and our v, and we're going to choose them basically in the same way. This is something that's easy to integrate, and this is something that's easy to differentiate. We know that the derivative of sine inverse is 1 over the square root of 1 minus x squared. So let's write that down. U prime is 1, therefore u is x. V is sine inverse of x, and therefore v prime is 1 over 1 square root of 1 minus x squared. And now we can use our formula. We get that this is u times v minus u v prime dx. So using what we've just obtained, x times sine inverse of x minus, and now x times v prime, so divided by square root of 1 minus x squared dx. And now we have this integral to solve, and here what we can do is we can use a substitution. We can say, okay, what I have here underneath the excuse me, underneath the square root, I'm going to call that t, and therefore dt is going to be minus 2x dx. Now if we write this out, we get x sine inverse of x minus, or plus, if I combine with the minus from here, 1/2 dt divided by square root of t. Let me just double check that it is right. Okay, so I get a minus that goes there, and then x dx gives me 1/2 dt. Okay, and now I can integrate. I get x. Let me actually continue down below so I have a bit more space. X sine inverse of x plus 1/2, and now integral of 1 over square root of t, that is the same as the integral of t to the minus 1/2 dt. So that's again something polynomial looking. I know how to integrate that. I get t to the power 1 plus this thing, so t to the 1/2 divided by 1/2 plus c. Now I can clean that up a bit. Sine inverse plus, and I'm going to make the substitution right away, 1 minus x squared plus a constant. So you see, in this case, we had to apply 2 rules to get to our answer. Integration by parts first, to turn our complicated integral into a simpler integral, an integral that we can solve with a substitution. So here t was 1 minus x squared. And then it was basically algebra and our rules that we already established to get at the answer. Okay, now let's see what else we have. I have to be a bit mindful of time, but I think we can do a couple more examples. Okay, let's maybe do let's do one example that's kind of complex. That's going to be a good way to work through an example where you have to use and substitution and integration by parts and a clever trick. So let's have a look at the integral of the secant function to the power 3 x dx. And at this point, you probably are tired of integrals of trigonometric functions, but let's press on, because this is yet another example of how you can approach problems of this form. So the first thing that we can do with this form is we can say, well, hey, I've got an odd power, so I'm going to write this as secant squared x secant x dx, and I'm going to hope that that gives me something useful. And indeed, it does give you something useful, because now you can use the fact that we've already used a couple of times, that secant squared of x is 1 plus tan squared of x. So you can write our integral also as 1 plus tan squared x times secant x dx. Okay, so now let's split that up. We have integral of secant x dx plus integral of tan squared x secant x dx. And at least one part of that is easy. So the integral of secant of x dx, we've done that last time, that is equal to the logarithm of the absolute value of secant of x. So secant of x plus tan of x. And that leaves us this part right here. And this, well, we don't have a form for that, so I'm going to call this I for integral. And we're going to compute what it is over here on the right-hand side. Let me just make sure I have enough space to write everything down. So now let's have a look at what this I thing is. So we get tan squared x secant of x dx. And there's a couple of things that you can do. There's a couple of approaches that you can try out. What you don't want to do is you don't want to replace tan squared by secant squared minus 1, because then you're going to go back to where we started from. But nevertheless, there's a few things that you can rely on. And one thing that we can sort of, if we see a bunch of tans and secants, we know that they are related by integration and differentiation. So we can try to bring this in a form where integration by parts is going to work. So for example, and let me write this down here on the side. So if we have tan x, as we've already seen a few times, the derivative of that is secant squared of x. And likewise, if we have secant of x, the derivative of that is tan x times secant of x. So those are tools in our arsenal. And now let's see if we can use those to crack this integral. And one thing that we can observe is that, hey, tan x times secant of x, that's kind of neat. That's almost what I have here. And well, on the other hand, well, I've got tan squared, so I've got another tan, and maybe I can do something with that other tan here. So in order to make that more concrete, let's write the integrand as tan x times tan x secant of x dx. So then I see something really nice happening. I have a tan x here, and I have a tan x secant x here. And why is that nice? Well, now I can use my integration by parts formula, and I can choose for my, in order to apply that formula, I need something that is easy to integrate for you. So something where I can easily find the integral. And what is that function going to be? Well, it's going to be tan x times secant. So I can call this u prime because I know what the integral of this part is. The integral of tan x secant x is just secant x itself. So we're going to call this thing u, and then we know that, so u prime, we're going to call that u prime, and then we know that u is the secant of x, because if u prime is d dx of secant, then u is secant. And likewise, we're going to call this thing v, because it is easy to differentiate, sorry, not v prime, v is easy to differentiate. The differential is just secant squared. Okay, so now we can pull everything together with our formula. We get that this is u times v prime minus integral of, sorry, uv. It's getting a bit late in the day. I make more mistakes than I'm used to. V prime dx. And we can substitute. So we said u is secant x. V is tan x. And then minus integral of u. So secant of x. And then v prime, what is v prime? It's the derivative of tan. It is secant square x dx. So now let's just write that a little bit more cleanly as secant x tan x minus secant to the power 3 x dx. And now, oh no, disaster, problem, big calamity. I was hoping to get some integral here that I could integrate really quickly, really easy, just like I could integrate this thing and this thing very easily. But unfortunately here, I've got something that is not easy to integrate. In fact, if I look at what I have here, I see that I've ended up with the thing that I started from way back in the beginning. And you might say at this point, hey, this is a disaster. I haven't done anything. I've just rewritten my integrand, but I haven't finished at all. At that, I will say not so fast. Let's have a look at what we have obtained. So I can put this aside, and now I can say my integrand right here, the thing that I had to compute is secant x tan x minus integral of secant to the power 3x dx. And if I now write down what my entire, where I started from, so I started from secant to the power 3x dx, and I obtained, well, first this term, ln absolute value secant x plus tan x, and then plus this integral that I called I, so plus secant x times tan x minus integral of secant to the power 3x dx. So that's what I've obtained so far. And this is pretty cool because now I can take this term and put it to the other side to get 2 times the integral that I wanted to compute is equal to logarithm of secant x plus tan x plus secant x times tan x. And therefore, if I divide by 2, I get that the integral that I had to compute is equal to 1/2 of that. So 1/2 ln absolute value of those two things plus 1/2 secant x times tan x plus a constant. And this is my final answer for the integral. And so you see the big lesson here is that we started from a complex integral, we transformed it and calculated it, and we ended up with another expression that involved the same integral, but you see there's a minus sign here, so those two integrals don't cancel out with one another. What they do is they give you an expression that involves the integral, and you can solve that expression to find the integral itself. And that's something that we'll see a couple of times now in these reduction formulas. This is something that happens in some cases where you can't solve your integral on the nose, but you can make it more simpler and therefore arrive at the result after a few steps. So that's going to be the last part for today. So I'm going to skip this slide. So we'll look at a few examples where this idea really comes out. So this is going to come under the header of reduction formula, because what we will obtain is formula to make a given integral simpler. Formulae to make an integral simpler. So it's maybe easiest to see this on an example, and let's start from computing the integral of x to the power n times e to the minus x dx. And here this n power, this is an arbitrary exponent. So this is an arbitrary exponent. So now let's say we want to calculate this integral for arbitrary n. So we'll call this I sub n, the integral for whatever this n is. And so now what we're going to have to do is we're going to have to find a way to drag along that n in our computations as we try to solve it. So one thing that we could try to do is we could try to use integration by parts here. And why is that a good idea? Well, keep in mind, we need something that is easy to integrate and something that is easy to differentiate. Both subparts here are equally easy to integrate and differentiate. But remember, if you apply the formula, you turn integral of u prime v into the integral of u v prime. And so in particular, if we choose for v x to the power n, then if we apply our integration by parts, we're going to have to integrate v prime. So we're going to get something x to the power n minus 1. So with a little bit of thought, you can sort of see if you apply integration by parts judiciously, we won't be able to solve the problem, but we'll be able to simplify it at least a little bit. So let's do that. And let me just go back to the notation and make sure I use the same notation. So here, if we use for u prime, if we choose e to the minus x, and therefore if we make x to the n into our v, what are we going to get? Well, and I'm going to do it in one step now. So I get u times v. So if u prime is e to the minus x, u is minus e to the minus x times v. So x to the power n. So this is u and this is v, and then minus the integral of u again, so e minus e to the minus x, and then the derivative of v, so n times x to the n minus 1 dx. So this is u, and this thing right here is v prime. So now let's clean that up a little bit. Let's write this as minus x to the n e to the minus x, and then plus integral or plus n times integral of x to the n minus 1 e to the minus x dx. So just some algebraic changes. Some minuses that combine to give you a plus, and now let's look a little bit at what we obtained from this manipulation. So we started from in, the formula for exponent n, and now we have some piece of function here, and then plus n times another integral. And now if you look at the form of this integral, it's precisely what we started off, except the exponent is no longer n. Now the exponent is n minus 1. So using our notation, we can say, well, what we've obtained here as the integral is I sub n minus 1. And that's an important realization. Let's write it down by itself. So we have that in is equal to minus x to the power n e to the minus x plus n times in minus 1. And this is an example of a reduction formula, because what you have is an expression for a complicated integral in as a function of a slightly less complicated integral. And you can use this integral, this formula, to find what in is for different values of n. So let's see this in practice. Let's start by I0. What is I0? Well, for this one, I don't have a formula, but I can calculate it explicitly. It's x to the power 0 e to the minus x dx. So x to the power 0, that's of course 1. And then we're left with the integral of e to the minus x. So we get minus e to the minus x plus a constant. And now, what is I1? Well, now we can use our reduction formula, and we get it's minus x to the power 1 e to the minus x plus 1 times, and then in minus 1. So for n is equal to 1, that's I0. So if we substitute, we get minus x e to the minus x plus, or sorry, minus, if I immediately simplify, e to the minus x plus a constant. So in other words, minus x plus 1 e to the minus x plus a constant. If I just combine the terms. Now, that gives us I1. What is I2? Well, again, we can use the formula. It's minus x squared e to the minus x plus 2 times I1, and I've already computed that, so minus x plus 1 times e to the minus x. And now I'm not going to write plus constant, I'm going to add the plus constant here. And I can simplify that a little bit, and actually let's do that all on the same line. I can write this as minus x squared plus 2x plus 2 e to the minus x plus a constant. And now I can keep doing that. I can write down I3 and I4 and so on up to arbitrary order of I that I want to derive. In this case, it's going to be difficult to find a closed form formula for what IN is. So if we look at what we've obtained so far, e to the minus x, x plus 1, e to the minus x, and then whatever this is, e to the minus x, there's no real regularity in there. So we're probably not going to find a closed form formula that we could then prove. But what we can do is, for instance, if we have to calculate I4, is we can use the formula 4 times to find I4. And then let's maybe do one more example of this, and then we'll be at time. And then for next time, I will leave integration by part. Sorry, not I will integration of rational functions. Yes, that I will leave to next time. So let's just do one more example. So for a second example, let's calculate again something that we'll call I sub n. There's the integral from 0 to pi over 2 of cosine to the power n x dx. And we've already seen that cosine to some power, that's something to be afraid of. So in some cases, that's easy to do. So if we have an odd power, then we can use a substitution. If we have an even power, then we have to use our double angle formula. But in general, it's a bit tricky. So here we have a related question. We're not interested in the indefinite integral. Now we're interested in the integral between 0 and pi over 2. So let's see if we can make some headway with this. So first thing that we'll do is we'll try to apply a substitution, or we'll see if we can work our way a bit towards that. Let's write this integral as integral from 0 to 2 pi. And now let's split off a cosine anyway. So let's write this as cosine to the power n minus 1 x, cosine x dx. And now this, like, it's going to depend on the power of n, whether we can make a nice substitution or not. But let's put the substitution idea on the side for a moment, and let's try to use partial integration by parts. So what I'll choose is, I'll put this equal to u prime, because it's something that I can easily integrate. The integral is minus sine, and I'll choose this to be my v prime. Again, my v, something that I will have to differentiate. And if I do that, well, now what do I end up with? Well, I have to integrate cosine of x, so I get minus sine x, and then times v, so cosine to the power n minus 1 x. And now we have a definite integral, so we'll also have to evaluate this between the bounds 0 and pi over 2. And now, what else do we get? Well, we get minus integral 0 to pi over 2. And integral of what? Integral of u times v prime. So u was minus sine x. So we get minus minus or plus. And then just move my zoom windows a bit. So times, now the derivative of v, so n minus 1 cosine n minus 2x dx. So what does this give us, or where does this come from? So this is v prime, and this thing right here is minus u, where, why is it minus? Well, because I took out minus and combined it with the minus. And likewise here, this is u, this is, of course, v. Okay, so that's our formula. Let's clean it up. Let's substitute the bounds. So we get minus sine pi over 2 cosine to the n minus 1 pi over 2 plus sine 0 cosine to the n minus 1 of 0, and then plus, I get a constant n minus 1, so I'm going to take that out, n minus 1 integral 0 to pi over 2 cosine to the n minus 2x sine x dx. And I think I forgot something. Okay, I made a small mistake here when I said the derivative of v is n minus 1 cosine n minus 2x. I didn't apply my chain rule completely. There's also a sine x dx that I have to add. So all of this together is the derivative of v. And that means that then here in the result, I get a sine squared. I get one sine here and another sine here, so sine squared. Okay. So this is good. What do these constant terms evaluate to? Well, we get a cosine pi over 2, that gives us a 0 here. We get a sine of 0 here, so that gives us another 0. So both of these terms in the front, they cancel, and we are left with n minus 1 integral 0 to pi over 2 cosine n minus 2 x sine squared x dx. And so this is kind of neat because now we have something that involves sine squared. So now let's try rewriting that as, let's write this as 1 minus cosine squared x. We're trying to say something about an integral that involves cosine. So let's try to make everything into cosine. So if we make that substitution, now we get n minus 1. And then we get integral from 0 to pi over 2 cosine to the power n minus 2 x dx minus n minus 1 integral, and now I get the part from cosine squared times cosine to the n minus 2, so that combines to give me cosine to the power nx dx. And we're almost there. Don't worry, the slide is almost full, but we're almost there. So if we look at what we have, here we see the same thing that we started from, but with n minus 2 in the exponent. So this is in minus 2 using our notation. And this is the thing, literally the thing that we started from, in. And so if we write down our reduction formula, what do we get? Well, you start from the left-hand side. In is n minus 1 in minus 2 minus n minus 1 in itself. And now we can take this term and bring it to the right-hand side and solve for in. And if you do that, you'll find that in is equal to n minus 1 divided by n minus 2. And this is useful because, again, it allows you to write down what the integral is for different values of n. So let's do that, and then finally we'll call it a day. And now the only thing that you need to keep in mind for the time being is that we go down in jumps of 2. So it's going to differ whether n is even or odd, but we'll see how that comes up in a number of examples. So let's start with I0. So I0 is the integral of cosine to the power 0 x dx, then anything to the power 0 is 1. So I0 is pi over 2. And what is I1? Well, I1 is the integral of cosine x dx. So it's sine x evaluated at pi over 2 and 0. Sine of pi over 2 is 1. Sine of 0 is 0. So 1 minus 0 gives me 1 for I1. And now we can use our formula to calculate I2. So I2 is 2 minus 1 divided by 2 times I0, or 1/2 pi over 2. And we can continue I3, and let me also maybe draw some lines. So here we have to use I0, and for I0 we have to go back to here. So we basically have to jump back 2 formulas to whatever this is. So I3 is 3 minus 1 divided by 3 times I1. So here I1 is what we calculated here, and we jump back to here. And so we get 2 divided by 3 times I1, so that is 1. And let's just do 2 more, and then I think you will see the pattern. So what is, now I need to move my zoom again. What is I4? So I4 is 4 minus 1 divided by 4 I2. So here I'm going to go look at this guy. So it's 3 divided by 4 times 1 divided by 2 pi over 2. And what is I5? So for I5, I'm going to have to use I3. And I get 5 minus 1 over 5 I3. So 4 divided by 5 times 2 divided by 3 times 1 if you want. And that gives me I5. And you can see, again, we don't have an exact formula for IN where I can give you a prescription to calculate IN. But what I can do is recursively, I can compute, to compute I7, I can compute I5. To compute I5, I can compute I3. To compute I3, I can compute I1. And so I can sort of use all of those partial results to get I for whatever value of n that I care about. So these are important formulas and they'll come back. For instance, if you look at Fourier analysis, where you have to compute integrals of cosine to some power times another function, you'll see that they come up in later stages as well. So with that, I think we are at time. We're a little bit over time, so I will stop sharing my screen. Thank you again for your attention. That exhausts basically our basic integrations techniques. On Monday, we will look at the integration of rational functions. And then I think we have about three good classes to go. So we'll finish on time 2 weeks from now. So that's it. It's for week 10 from my side. I wish you the best for the rest of the week, and I will see you again next Monday. So bye everybody, and have a good rest of your week.
Thank you, Professor.